Okay, everybody, we have viewed two-wire control. Now we'll go and take a look at three-wire control. If I'm in three-wire control, logic input 1 must be my stop. And if you look at the stop, these pilot devices or push buttons associated with the wiring are a momentary contact, normally closed and normally open momentary contact push buttons, whereas these are maintained contact push buttons. So if you look at this, if I'm not pushing this stop button, 24 volts is present on logic input 1, which means that when you want this drive to stop the motor, you push on this push button, you interrupt that 24 volts, so we don't see 24 volts there, or we could say logic input 1 is now false because it's a 24 volt input. We start to stop the motor with whatever stopping method you've determined. Whereas logic inputs for forward and reverse are both normally open. So it requires 24 volts in order to start the motor, but it's an interruption of 24 volts to stop the motor. This gives us kind of a fail-safe or monitoring in our wiring. If you can imagine, a lot of things around motors are subject to vibration. So if a wire were to come loose here, and you had to close those contacts in order to make it stop, you wouldn't know that that wiring had failed until you went to stop the motor because it wouldn't stop, which would not be a very safe way to do the stopping for a motor. So that's two-wire control and three-wire control. We are going to now jump to page 34, and I'm going to talk a little bit about references. So a drive takes an input signal, 0 to 10 volts or 4 to 20 milliamps, and then scales that to whatever frequencies you've set. So if we had a 0 to 10 volt signal scaled to a 0 to 60 hertz output, then if I had an input voltage of 5 volts, you would all say that, well, you're going to have an output frequency of 30 hertz because that's halfway and that's halfway, and that's how it works. That incoming signal is referred to as a reference. And in this particular drive, we have two different references. We can switch between those references. They can be voltage or current, depending on which input you've wired them to. Not everything is as interchangeable as we might like it to be. On to page 38. This is in the beginning of the functions menu. And if we take a look here, this is, well, we know the constant torque or linear torque curve is just that straight line going up where voltage and frequency are increasing at the same rate. But here we have an S ramp and a U ramp. And what they do is they can change the shape of that curve just a little bit, or we can exaggerate them even more on either ramping up or ramping down. Same with our U ramp. Where this becomes useful is with special types of loads. So if you can imagine, if I have a conveyor full of empty glass bottles and I want to get that conveyor belt moving with those bottles on it, we can't just start full speed with that conveyor because the bottles are going to crash into each other and smash on the floor and make a big mess and downtime, loss of production. So what we're going to do instead, if we apply this S ramp, is we will slowly increase the torque until everything is moving. Once things are moving, we're going to increase the torque at a much higher rate. But then as we approach our target speed, we're going to decrease that rate of acceleration again so that we don't have that same, it'd be like getting up to the speed limit on the freeway, 90 depending on where you are, and just foot to the floor, and as soon as you hit 90, jam it on the brakes to make sure you don't overshoot it. So this allows us a nice smooth acceleration up to our target speed. And the U ramp does just like it looks like here. We can create a belly in that line, either above or below on acceleration or deacceleration. Let's go to page 40. Stopping modes. So different drives have different stopping modes available to them. This drive, we have a ramp stop, which is basically just your deacceleration parameter. We have a fast stop, a freewheel stop, and DC injection stop. You can select different stopping methods and apply them to different logic inputs. So we can essentially have two different stopping methods. We could have a freewheel stop and a DC injection stop for an emergency stop type situation. For the DC injection braking, we can control the voltage that goes in the event that we are DC injection braking, how much voltage we're going to apply to that. Next, we're going to move on to page 44. Now, this is a table, and I hope that the shape of these numbers here looks familiar to you. This is essentially a binary counting from 0 to 15, which gives us, with this drive, the availability of 16 different preset speeds. Now, preset speed, again, is predetermined speed that we want that motor to go at, independent of load or change in operating conditions. So in order to have the drive cause the motor to move at the speed that we've set for preset speed 5, we need to have 3 logic inputs in use. This logic input, or the most significant bit of our binary number here, needs to be true or have 24 volts present, and then these two need to not have 24 volts present, and that will engage preset speed 5, which could be 100 hertz, could be 75 hertz, could be 2 hertz. We don't know. That's going to depend on the application. Carry on to page 76. So these last 2 pages we're going to look at. Let's back out here. Basically, this is just a list of functions or an index of functions that we have. So probably more useful if you're dealing with a paper copy of the manual. But if you're looking for jog operation or DC injection with a logic input, what page do I go to find that? And right before that, we have an index of parameter codes. So you might, for example, get a question asking you about parameter RPT. If you can't find it in the manual, flip right to the back. These are alphabetical. Find it, and that's the page number you go to. So there you have it. I hope you learned something, and we will talk to you soon.